Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain, Professor of Chemistry at Jivaji University, Gwalior. Today I shall take up Instruments for Analysis Part 3 under the paper Fundamentals of Analytical Chemistry. Today our learning objectives are how by absorption of electromagnetic radiation quantitative analysis can be done. What are the laws for quantitative analysis? What are the limitations of quantitative analysis? Is reasons for deviation from the well-pronounced laws and fluorescence and phosphorescence. So in the first I shall tell you when electromagnetic radiations strike the substance passes through a solution, certain portion of it is absorbed, certain portion of electromagnetic radiations absorbed and its intensity is decreased. So by the measurement of that decrease in intensity, we measure the concentration of unknown substance, or we can say the decrease in intensity is directly proportional to the concentration of the unknown substance. So this is done by calibrating the instrument and by taking a monochromatic radiation of light. Monochromatic means a particular wavelength or a band of wavelength of the polychromatic light, which we obtain by passing through a monochromator. Monochromator may be a prism or it may be a diffraction gratings. By passing through that, we may select a wavelength of our choice. The intensity of a collimated beam is proportional to the number of photons per second passing through a unit cross section. If the photons which strike the sample possess energy equal to that required to cause a quantized energy change, absorption may occur. The absorption thus decreases the intensity of the transmitted radiation. Scattering and reflection also lower the power of the radiation. However, for most systems which are studied, these losses are small compared to absorption. Here, first I shall discuss quantitative laws. Consider the changes in intensity of electromagnetic radiation which occur when monochromatic radiation passes through the absorption cell as shown in figures 1. The cell is first filled with a blank solution which consists of the solvent plus sample constituents other than the principal absorbing species. With this blank solution in the cell, the intensity of the transmitted radiation represents the incident intensity minus that lost by scattering, reflection, and any absorption by other constituents, which is very small. This intensity is denoted as I0 because it is corrected incident intensity when the blank is replaced by the sample. Let us consider what happens to the radiation as it passes through segment A of the sample using the different notations of calculus. Di represents the decrease in intensity in an infinitesimally small layer dB, that is the amount of radiation absorbed in this layer. You can very well see this in figure 1. Here it is assumed that the absorption of energy by the matter requires a physical interaction between a photon and the matter. As a result, the number of possible collisions occurring in this layer is proportional to both the number of absorbing species in the layer and the number of photons passing through it. Thus, the loss in intensity Di is directly proportional to n, that is, the number of absorbing species, and I, the number of photons per unit cross-sectional area per second. For layer dB, the number of absorbing species is given by the expression where n is equal to 6.02 into 10 raised to power 20 species per millimole into C millimole per ml into dB into x into y ml, where dB, x and y are the linear dimensions of the layer, assuming that 1 cc is equal to 1 ml. Since x and y are constant, above expression reduces to n is equal to k dash cdb, where k dash is equal to 6.02 into 10 raised to power 20 into x into y species centimeter square per millimole. The number of collisions is proportional to the product n into I, or dl is proportional to ni is equal to k dash ICdB. Therefore, di is equal to minus k ICdB. Equation 1. K is proportionality constant. The negative sign is introduced because intensity decreases as dB increases. Integration of equation over the entire cell length B gives the loss in radiant power due to absorption by sample. Separating the variables in equation 1 gives integral it to I0 di upon I is equal to minus k integral b to 0 c dB. After solving the equation, it comes out to be ln it upon I0 is equal to minus kbc. And converting from natural logarithm to base 10 logarithm, one can obtain 2.303 log it upon I0 is equal to minus kbc, or log it upon I0 is equal to minus k upon 2.303 bc is equal to epsilon bc, and this is equation 2, where epsilon is defined as the molar absorptivity, also called as the molar extinction coefficient, a very important parameter reflecting the absorptive power of the analyte. If the concentration is given in grams per liter, E is replaced by A, the specific absorptivity. The term IT upon I0 is defined as the transmittance and represented as T, which is the fraction of the incident radiant power transmitted by the sample. The percent transmittance is defined as 100 into 10. Therefore, from equation 2, log T is equal to epsilon Bc, or log T is equal to epsilon Bc. Minus log T is also defined as the absorbance, represented as capital A, or optical density. Thus, minus log T is equal to A is equal to epsilon Bc, and this takes the form of the equation 3. The value of epsilon is characteristic of the absorbing molecule or ion in a particular solvent and at a particular wavelength. The value of epsilon is independent of concentration and the path length of radiation. Equation 3 above is referred to as the Beer-Lambert law, or more simply as Beer's law. In the derivation of this law, it has been assumed that the incident radiation is monochromatic. The absorbing species act independently of each other in the absorption process. The absorption occurs in a volume of uniform cross section. Energy degradation is rapid, no fluorescence occurs, and the refractive index is independent of concentration. For multi-component systems containing more than one absorbing species. It is assumed that the species act independently of one another and that their absorbances are additive. From figure 2, we can see that absorption spectra of species 1 and 2 and their mixture. At the absorbance of maximum for X is lambda 1 and Y also has an absorbance at the absorbance maximum for component Y represented as lambda 2. Component X also absorbs radiation. The absorption spectrum for a mixture of X and Y is the sum of total individual curves. Equations for the total absorbance at each wavelength are as follows. These equations are represent lambda 1 for species 1 and represent as concentration 1, and for species 2 it represents as C2. Equations can be very well seen from equation 4. And the figure 2 represent the spectra of two components and the spectrum of a mixture of the two components. So as per Beer's law, the absorptivity of both the species 1 and 2 has been added, and after adding we obtain the equation 4. From equation 5 again we can see that for sample 2 it is lambda 2, where A represent lambda x and A represent lambda y, observed absorbances of the mixture at wavelengths lambda 1 and lambda 2 respectively. And these are for the component 1 in the mixture at lambda 1 and lambda 2. Absorbances of component 2 in the mixture again as lambda 1 and lambda 2. And if we combine the molar absorptivity of components 1 and 2, they are taken at lambda 1 and 2 respectively. Cx and Cy are the respective concentrations of the component 1 and 2 in the mixture. In general, if there are n components, because it is not only that we can take two components, it can be multi components, it may be three components, it may be four components. So we have represented here as n components. The total absorbance expression at any wavelength A takes the form as A lambda is equal to summation of all A n to power lambda is equal to B summation of n epsilon n power lambda concentration of n. Here, instead of sample 1, sample 2, sample 3, it has been represented as n component. So, in the above equation, n has been given number instead of sample 1, sample 2, sample 3 or species 1, species 1, species 3. I have represented here as n numbers. N indicates the number of samples which have been taken and summation of which or the addition of which gives the total value. In principle, n absorbance measurements at n different wavelengths are required to determine the concentration of n components in a mixture. Most of the absorbing species follow laws of absorption, that is Beer's law. But some of the substances, when concentrated, they deviate from the Beer's law. You can see from the figure that this figure is not a straight line, but it is a curved line. Plot is curved. This curvedness in the plot is known as deviation from the Beer-Lambert law, because it should be a straight line. Why these deviations? These deviations may be due to two reasons. Reason number one, it may be due to the aggregation of the molecules of the analyte which we have taken. That is, when radiation passes through it, then the refractive index of the medium may change. Due to that reason, there is deviation from the straight line, which is known as deviation from the laws of absorption. Another reason for deviation may be due to the instrumental reasons. Instrumental reasons may be there that due to fluctuations in the instrument which we may observe, or it may be due to the stray radiations passing through the instrument. And the reason for that, we can very well estimate the substances quantitatively in the concentration range from 10 raised to power minus 2 molar solutions to 10 raised to power minus 6 molar solutions. If solution is concentrated, then 10 raised to power minus 2 molar, then aggregation will be there, then its refractive index of the medium will change, and then the plot will be a plot between absorbance and concentration will be a rounded curve or a curved structure. It will not be a straight line, and it will be a deviation from the Beer's law. Reason for terminate instrumental variations which cause apparent deviations are as follows. Stray radiation reflected within the instrument, sensitivity changes in the detector, and power fluctuations of the radiation source and detector amplification system. However, double beam instruments cancel out most of the random causes of deviation. Figure 4 demonstrates that the shape of the calibration curve often depends on the band width. Two wavelength bands of equal width are designated lambda 1 and lambda 2. The best wavelength for quantitative analysis is lambda 1 due to two reasons. First, at the absorption maximum, the change in absorbance with concentration is at a maximum, yielding greater sensitivity and higher accuracy. Second, within this band, the molar absorptivity is relatively constant and a linear calibration curve is obtained as shown in figure 4b. However, if a wavelength is selected on the side of an absorption peak, for example, lambda 2 in figure 4a, the molar absorptivity varies across the band. At this wavelength, the system does not follow Beer's law and a curved calibration is obtained as shown in figure 4c. Chemical equilibrium. An absorbing species which is involved in a chemical equilibrium may exhibit apparent deviations from Beer's law. For example, of such systems are presented below. An aqueous solution of a weak acid HB, which has an absorption maximum at lambda 1. The anion of the acid B is non-absorbing at lambda 1. HB is involved in the equilibrium. HB in equilibrium is H plus B minus, for which the mass expression is Ka is equal to H plus in bracket B minus upon HB in bracket. The analytical concentration indicated as CHB includes both forms. That is, form in ionized form, B anion, and in combined form, HB. As long as the ratio HB upon CHB remains constant, Beer law is valid when using either HB or CHB. But this ratio depends on the pH of the solution. If protons are less than the value of Ka, the acid exists primarily as HB and there is no problem. However, in unbuffered solutions, the fraction dissociated changes with pH, which in turn is a function of total concentration CHB. Such a system will show an apparent deviation from Beer's law if CHB is used as the concentration. The intensity of fluorescence or phosphorescence is proportional to the electromagnetic radiation which, which is absorbed by the species and represented by the following equation, where IF, I0 and IT are the intensities of the fluorescent, incident and transmitted beams respectively, and K is a constant which is a function of the quantum efficiency of the fluorescent process. For this, Beer's law is given by the equation 12 as given below. Substitution of equation 12 into equation 11 gives following equation. Exponential term in equation 13 can be expanded as a Taylor series yielding equation 14. From the equation 14, it is quite clear that if ABC is greater than 0.05, all the bracketed terms in equation 4 except the first becomes negligible, and one can write IF is equal to K dash I0 ABC, that is the intensity of luminescence. Luminescence represents both phosphorescence and fluorescence. It is proportional to the intensity of the incident beam, the absorptivity of the species, the path length in the cell, and the concentration of the species if ABC is greater than 0.05. So I may conclude that today we have learned how by absorption of electromagnetic radiation we can find out the concentration of unknown substance. Similarly, by measuring the intensity of fluorescence and phosphorescence, we can find out the concentration of substances which can fluoresce and phosphoresce. This is a unique feature of this experiment, that we can simultaneously find out the qualitative way what is the unknown substance, and we can find out the amount of unknown substance. In this experiment, lambda max is characteristic like the boiling point, melting point. It is an energy parameter which is characteristic for each and every substance. It is fixed, it will not change unless experimental conditions change. Lambda max is qualitative parameter of analysis, and the total absorption or transmission is the quantitative parameter of analysis. So lambda max is an energy parameter, whereas this is a absorbance is quantitative way how much amount of that substance present. Another unique feature of this law, Beer's law, is that if more than one substance is present in the solution, two analytes are present, analyte A, B, C, three analytes are present, then all the three can be simultaneously determined. By lambda max, all the three can be identified. All the three can be identified qualitatively. The unknown substance can be identified, and also by the additive nature of absorbance, we can find out how much each of these substances are present. Also, by using ultraviolet visible spectroscopy, the principle of which is based upon Beer-Lambert law, we can find out the conjugation in the given compound, conjugation in the given organic compound by simple calculation as per Woodward law. We can calculate the conjugation and we can find out how much conjugation is present in that molecule. This is for finding out the conjugation. UV visible spectroscopy is a very important type of spectroscopy. Another important feature of UV visible spectroscopy based upon Beer-Lambert law is its feature is extinction coefficient or molar absorptivity, which is different for each compound. It tells us how much intense is the absorption. If we form a complex of transition metal with some ligand, then we use that complex for the analysis of particular metal ion. If the color is very dark or light, that idea we get from molar extinction coefficient. For example, if I have to estimate lead by complexation with dithiazone, very deep yellow color we obtain. So by measuring its extinction coefficient, we can find out how much dilute solution of lead we can estimate. So it is, if extinction coefficient is very high, it indicates that we can measure dilute concentrations of that particular ion. So this is the one of the unique features of the UV visible spectroscopy. Thank you.